on my iPad because I feel like Heinrich did not show my favorite sheer thickening movie, and he's selling himself short because this actually came from a student from the University of Chicago. So this was done by Rob Deegan. Did Rob do this while he was at Chicago, or is it?
No, with Harry Sweeney.
With Harry Sweeney. Okay, so this was after Rob left Chicago. So this is a sheer thickening fluid. This is cornstarch and water, and you can, like I said, you can find this on YouTube. I don't know what my passcode is. Okay, and good. Okay, and it's a petri dish. The petri dish is just vibrated from below. Okay, so I'll just play that. Hopefully this will go. It's just TV connected. This is the first time I've ever attached my iPad to something. Okay, so here they made a little hole in it. They showed the hole is stable, but this is not the interesting part. Okay, so you can see you get all these structures. These holes move around. It does things that don't really look very Newtonian. But in a minute, what they're going to do is they're going to change, I think, either the amplitude or the frequency of the shaking, and you'll see something very unusual happens in this system. So make sure. Okay, here we go. So frequency and amplitude. Okay, so they put a little perturbation with a straw, unfortunately, and you see what happens is these things grow, and they keep going. Wow. This is very
The blowing is still happening?
The blowing is not happening. So they took a straw and they blew a little perturbation on the surface, and then they went away. And now all they're doing is they're shaking cornstarch at some frequency. So you can see this shear thickening. You get all kinds of bizarre behavior that I don't think anybody's explained this yet, have they? I mean, I think this is an open question. What the heck is going on in this system? Okay, so if you Google, I think it's cornstarch and Rob Deegan, you can get that on YouTube.
Another, my favorite,
yeah,
is the same experiment, but they have the dish sitting on a base speaker, and they're playing right now.
Oh yeah. So you can do that. I think that one's also on YouTube. So if you can find all these things on YouTube. Okay, so let's see. How do I turn this off? I'm just gonna unplug this. Okay, so I said this is all can I just put this over here to turn this off? Okay, so I had some questions that I promised to answer from last time. So the first was somebody asking about the swimming efficiency of fish. So swimming efficiency. Okay, and just to recall, last time we said for microorganisms, it's typically a couple percent the swimming. Okay, so for fish, the measure is not exactly the same if you look in the literature. Typically, they use something that's called the food efficiency. Which is roughly defined as some sort of average thrust. Right, so it's averaged over one stroke. So if the fish's tail is doing the average over stroke times the velocity over some average power consumption. Okay, so it's actually very close to the definition that we had last time, although not exactly the same. Okay, so I before my computer died, I went online and looked this stuff up, and there's a nice paper by Frank Fish and George Lauder. Yes, Frank Fish really does study fish. Frank Fish and Lauder. Okay, and so they in this paper they studied large fish, things like whales, and so I should say they did not define which efficiency they used in this paper, right? So there were no equations. I'm assuming it was something like fruit efficiency, but I'm not 100% sure. They found efficiencies that were between 75 to 90%. So huge efficiencies, all right? And again, I don't know exactly what definition they were using, but it's clearly bigger than 1 or 2%. The other data I had, and this is the data that I happen to have on my previously living laptop, is that there's a nice plot by Mark Jenny. And this is out of a paper that he had in Science in the 80s. And like I said, I don't reference right now, but it came out somewhere around there. And the plot looks like this. So on this axis, he had the mass of different organisms, and on this axis, he had an energy per mass per distance traveled. So that's energy per mass per distance. And it was a log-log plot, and you see that there's a few lines. There's a line here for swimming. And then there's something for running. And then there's something for flying. And then you got a bunch of data points with different names. Okay. So I figured, well, I'll just take, and this data that he has here, this is measured data, so it's not computed, this is metabolic data. So what they do is they put this animal on a treadmill or something, and they measure the oxygen consumption. So this is really total amount of energy that this thing is consuming, including whatever efficiencies are going on inside your body. Okay. So if you didn't, so I took a point in swimming, and I looked up numbers for sardines, because that point happens to be about the size of a sardine. And I said, well, let's use something close to the definition of efficiency that we had the last time we talked. So I said, okay, so eta is going to be some force, the force to drag your sardine through the fluid, times your average swimming velocity divided by the average power consumed. So this is now power consumption. So I said, well, to drag the sardine, it's going to be 1/2 CV rho b squared A, some cross-sectional area. And this, the power consumed, I can read off this plot, right? So this, what can we call E? So this is going to be E times, this is per mass, so I need to multiply by the mass of the organism, times this is per distance, so to get a power, I need to multiply by a velocity. Oh, and the velocity up here too. Good. Okay, and then I said, well, CD for sardines, I said CD for sardines is about 1, which is pretty reasonable. I said sardines have a density of water, and I said my sardines were cylindrical. So there's my cylindrical sardine, something like that. Okay, and so then you get a nice thing that the efficiency should look like. So my V's cancel, my rho's cancel with my M, and this is going to end up being V squared times 2 E L. Okay, and so you can look up all those numbers online. And it's unfortunate I can't show you the plot that I found, because the plot, actually to find sardine velocity, I found somebody who had measured the velocity of sardines, if the velocity in sardine length per second as a function of the size of sardine. And it's a straight line. That's right about 1.5. Because remember last time, the part that I wouldn't let you record, I said the velocity of animals is their length per second. Works for sardines. Okay, so that's great. So you put in all of these numbers, and you get something that's about 40%. And so again, something much, much, much larger than the 1 or 2% we were seeing at low Reynolds numbers. And again, this also has all of the metabolic efficiencies in it, right? Which says that, okay, so if half of this is going into metabolism, then maybe you're actually kind of close to these numbers that Lauder and Fish reported. Okay, so that was answering the first question. The other question you guys asked was, let's see. So we were looking at drag, and we said, okay, if I drag on a sphere, okay, so we had a plot that looked like this. V drag versus the Reynolds number, and we did some dimensional analysis to show and saw the measured data look something like this. Right, something like that. Okay, so and what we found was that this transition was, if you look at the experimental data, this was at about 100. So you guys asked, well, why isn't that transition at 1? Right, should be at 1. Okay, so let me put some more points in here. Let me draw this better. So it turns out there is a transition that happens at 1. Okay, so let's say this is. So let's say this is 1, 10, 100, 1,000, and the 4th, and the 5th. Okay, so in this regime, everything was laminar. So that's what we predicted from our scaling, right? And so the flows look something like this, if that's your sphere. They look something like that. Okay, out here, what you noticed, all right, so at about 100, you kind of get to something where, so this is where our scaling worked well in the high Reynolds number limit. And over here is something where you get vortex separation. vortex shedding. Right? So the sphere is kicking out the vortices behind it. The transition that happens at 1, because you said, oh, this transition should happen at 1, there's actually an intermediate regime here. And in the intermediate regime, this is where you have vortices, but they're attached to the sphere. Okay, so these are attached vortices. Okay, so your flows look something like this, and you've got these sort of, I'm not going to be able to draw it well, but you've got something, streamlines that look like that, going around the sphere. Okay, so remember in our scaling analysis, what we said is that in order to get this regime, we neglected viscosity. And so what that tells you is when these vortices stay attached, viscosity has to be part of the calculation. Okay, and then again, viscosity comes in again over here where we get, this is where the boundary layer comes through. Okay, so that was Dragon Sphere. Pretty good on that. Okay, and then the last question was on why you don't see velocity in the Taylor paper at lowest order, and I haven't done that one yet because I was running around fixing my computer. So I'll tell you the answer to that one next week. Okay, good. So anything else, or should we go on to today's topic? Okay, so today we're going to do crawling, which happens to be, in some cases is a fluid dynamics problem. And I got interested in crawling when I had a student who got interested in snails. Here's a snail. Okay. And snails are actually interesting in the way they move, because snails, when they move, they secrete a thin film of fluid. Okay, so there's a thin film of fluid that sits underneath the snail here. Right? And then your substrate sits here. Okay? So this is fluid. Okay, and when the snail crawls, the foot is never in contact with the substrate. Okay, so the only way that the snail can generate propulsion is by generating stresses within this thin film. So in order to understand how this thing moves, you have to understand the stresses in the thin film. Okay, so first let me just give you a little bit of introduction to thin films. And actually this is going to tie in very nicely with what Heinrich was talking about, because in the end we're going to get to non-Newtonian films. Okay, so let's see. So thin films. Okay, this is hydrodynamics. This is hydrodynamic class. So first we have to talk about the Reynolds number. So the Reynolds number, as you know, is the relative importance of inertial and viscous effects. So right, we're going to the equation. Okay, so what I'm interested in is I'm sort of interested in the relative sizes of these two terms. Okay, and in thin film you have to be a little bit careful because there's more than one length scale in the problem. So, for example, if this is substrate, here's my film. There's some characteristic thickness, which we'll call h. There's some characteristic length scale in this direction, which we'll call L. And the velocity force, there's going to be two components as well. There's going to be U and a V. And the vertical velocities are going to be much smaller than the horizontal velocities, just from conservation effects. Okay, so if we just do a quick calculation to figure out what kinds of Reynolds numbers are going to be important. So this guy becomes something on the order of rho u squared over L. Right, and if I want to neglect inertia, so this would allow me to neglect inertia, then I have to compare that to mu over h squared. Right, and so I rearrange that, and I end up with h squared over L squared. Okay, so your criteria is actually this. In order to neglect inertia, you have h squared over L times the Reynolds number must be much less than 1. So this is actually very nice because it's a much less strong condition than just saying your Reynolds number is small. Right? So and let me give you an example for snails. So in snails, this thickness here is on the order of 10 to 20 microns. Okay, and the characteristic length at which the snail is forcing, sort of sending signals through this film, this characteristic length is about 1 millimeter. Right, so which tells you that for a snail, this guy is on the order of 10 to the minus 4. Right, so you can actually get away with having a reasonably large Reynolds number and still neglect inertia in all of your analysis. Okay, so that's what we're going to do.
Sorry, can I just clarify something?
Oh, yeah,
I guess
sure.
I didn't hear you, but
Yeah.
what is that L that you're defining is not the length of the snail. It actually
Yeah,
is
right.
in contact. Right?
Exactly. Yeah, good question. So it's the length of the characteristic disturbances that the snail puts into the film. Okay, so if you didn't know anything about snails, your first guess might be that it's the size of the foot.
Yeah.
It turns out, if I could show you the movie, that snails actually, if you look at the snail's foot from below, okay, so here's the bottom of the snail's foot, as the thing crawls, there are little waves that move along there. So that length scale, this 1 millimeter, is sort of the characteristics, of the waves that move along the snail's foot. Hopefully that movie will be available tonight. Okay, so, good, so let's just do a calculation. All right, so I'm going to start by doing one calculation which is not at all how snails move, and then I'm going to move on to real snails. Okay, but I'm going to do this other calculation first because it's analogous to Taylor's swimming sheet. Okay, so this is a waving sheet near a boundary. Okay, and this is analogous to Taylor's sheet. Okay, so the calculation I want to do is the following. Okay, so suppose I have a substrate. My substrate is going to be flat. And now I'm going to put a waving sheet on top of this substrate. Something like that. I'm not going to make it sinusoidal. I'm going to make it some arbitrary shape. Okay, so the shape of this sheet is going to be some h of x and t. And that shape is selected by the snail. So the shape is going to be some input that you give this problem. Okay, so this is the fluid here. And this is my snail, which I'll put in quotes. The snail can't really do this. Okay. Okay, and the one thing I'm going to tell you about, so I should also tell you the sheet is inextensible. So it's inextensible, so I don't want to have to think about elasticity. Okay, and for simplicity, I'm going to put in a traveling wave, which is typically what these organisms do. Okay, so I have something like this. So sometime later, it might look like this. Right, and I'm moving along here with some wave velocity. Okay, so you can already see that this is probably going to generate propulsion, and here's why. Okay, so if I take this little bump and I move this way, what this is doing is it's taking the fluid here and squeezing it into a small gap. So if you take this fluid and squeeze it into a small gap, that must mean that you have a high pressure on this side. Okay? Conversely, on this side, you're exiting a small gap and going into a large area, which means that you must have a low pressure on this side. Okay, so now I have a high pressure over here, a low pressure over here, that's acting perpendicular to these two interfaces, so it's going to end up pushing your snail that way. Right, so you expect to see a snail velocity going this way. Okay? Okay, so now let's just do the calculation. All right, so in my notation here, hat is dimensional variables. Okay, so all right, so we'll start, of course, with Navier-Stokes. Okay, so we're going to start with Navier-Stokes, but we've just decided that inertia is negligible, so I get rid of this. So I'm just going to balance these two guys. And of course, in a thin film, the gradients in this direction are going to be much larger than the gradients in this direction, so I can get rid of the x derivative here. And so what you're left with, and this is a very typical thin film equation, is dp dx is equal to d squared u dy squared. And that's it. And I've rescaled pressure to get rid of my viscosity. Okay? Everybody happy? Okay. And then the other one is going to be dq dy is equal to 0. And again, this is very typical in thin films. So in thin films, typically the pressure varies along the thin film, but not across the thin film. All right, so, and I need boundary conditions. So here are my boundary conditions. I get my boundary conditions for here. In the lab frame, my snail looks like this. So I've got zero velocity over here. I've got this guy moving in this direction with some snail velocity, Ps. Okay? And I have a wave velocity, and the wave velocity I measure in the frame of the snail. So imagine your snail is some kind of a robot or a device where you turn on a motor and it generates a wave moving at a certain speed, which means that there's going to be a wave speed that goes this way, which is going to be v wave minus v snail. Right? Okay? So then, of course, you have to go into the wave frame. So what I'd really like to do is I'd like to make this boundary stationary, so I don't have to worry about that deforming. So in the wave frame, this now becomes, so this now becomes v wave minus v snail. This thing is now not moving, right? So this has zero velocity, and then this guy goes in this direction at some velocity v wave. Okay, and then the last thing I'm going to do is I'm going to normalize everything by v snail. Okay, so my dimensionless, so this is now dimensionless form. Okay, so in dimensionless form, this thing becomes. So I'm moving this way at 1. I'm moving this way at 1 minus v snail. So my dimensionless snail is v snail divided by v. Good. Okay, so now I have everything that I need. So now I just have to integrate this guy twice, apply these boundary conditions, and I'll get something for velocity. Okay, so just do that. Okay, so I integrate this guy twice. So pressure is not a function of y, which means I can integrate this guy twice with y. And I end up with u is equal to minus dx, and I'm going to have 1/2 y times y minus h. And then I'm going to have to satisfy this boundary condition. So that's going to give me a v snail. I have to get my sign right. I better get my sign right. So that's going to give me v snail times y over h minus 1. Right, that's that boundary condition. And then I've satisfied the top boundary condition, so that's going to be plus 1. Okay, so all I did was integrate twice, apply boundary conditions. All right, so this is my first equation. So this is conservation of momentum. Okay, that doesn't tell me much because I still need a pressure. So what's the next thing I should apply? I could assign you this problem right now. So what would you do next in this problem? Oh, this is good. Okay. So if we apply conservation of momentum, what else do you have to do? Nobody knows. You just solve Navier-Stokes and then you're done. What else do you want to conserve in this system? Mass. Mass. You have to conserve mass. Right. So we need to say something about conservation of mass. Okay, so conservation of mass is also very easy in thin films because, so if I go over here where this boundary is stationary, right, I mean the shape is stationary, then if I look at the fluxes, the flux through here has got to be the same as the flux through here, and it's got to be the same as the flux through here, right, because there's nowhere else for the mass to go. So that means that Q, the flux, Q has to be a constant. Okay, and so I can write down what the flux is, so it's going to be the integral from 0 to 1, because I've normalized this by h. Oh no, sorry, it's going to be the integral from 0 to h of u dy. So I have an expression for u. H is not a function of y, so I can just integrate this. I have all my y dependence explicitly, and I'll just write down what the answer is for you. Okay, so this, you do this integral, you find that Q is equal to minus 1/12 dx times HQ minus H v snail plus H. Okay, this is Q. Q is a constant. And I can rewrite this to solve for dpdx. Okay, so now I have an expression for dpdx. So dpdx is going to be equal to 12 over h cubed minus h times 1 minus v Snail over 2 minus q.
That's okay.
Okay, that's another useful equation. Okay, so this came from conservation of mass. Okay, but I'm still not done, right? So what do I know? What am I trying to solve for? I'm trying to solve for v Snail. This is v Snail. Right, so that's okay. I need to keep my v Snails in here. I now have another expression for dpdx, but I've traded it for something else I don't know, which is q. Okay, so what else? I've now used conservation of momentum and conservation of mass. What else can I use?
For Q?
For q, yeah. What else has to be true in this system? Okay, so what did we say? So let me give you the easy one, and I'm going to let you think about what the harder constraint is. Okay, so so the other thing I'm going to say is I'm going to, since I have a dpdx, obviously at some point I'm going to have to integrate an x to get a pressure, which means I'm going to need boundary conditions in x. Okay, so the boundary condition I'm going to apply is I'm going to say that this thing is periodic in x. Okay, yeah.
Isn't there something about Q being the thickness of the film times the velocity of the snail?
Oh, Q being the thickness of the film times the velocity of the snail.
Because it's basically laying down so much slime at a given time.
Right, so I guess, the Q is related to how fast the snail is producing mucus, but you don't necessarily know what that is. Right, so in this case, we're gonna assume that the snail is making this fluid as fast as it needs to maintain this steady state. So certainly, once we've done this calculation, we're going to come out with a number for Q, and then the snail has to produce the fluid that fast in order to crawl using this method.
But I mean, you can see how much mucus is left behind, and that tells you what the production rate is.
In an experiment.
Yeah.
Right. Okay. So we're going to use a theoretical snail in which we don't know how much is left behind.
Okay.
Yeah. Good. It's a good experimental solution to the question I asked. Okay. All right. So I'm now going to apply the periodic boundary conditions. But while I'm applying the periodic boundary conditions, you have to think about the last condition that we need. And I told you what it was at the last lecture. And when I wrote down for swimming in microorganisms, I said, here are the equations of motion, and you need to conserve momentum, you need to conserve mass, and you need to do one more thing. So while I write down what happens, what you get from periodicity, you can remember what that last condition is. Okay, so periodicity tells me that P of 0 is equal to P of 1. So I've renormalized it. So I've rescaled everything. So this is at 0 and this is at 1. I should be drawing that on the dimensionless plot. I will. 0. Okay. So if this is true, I can write this in a funny way. I can say, oh well, 0 is equal to the integral from 0 to 1 of dp dx dx. Okay? And I have an expression for dp dx. Right? And in this expression for dp dx, all I have in here is 12, which is a number, h cubed, which I know what that is as a function of x, because that's what I put in. It's my input shape. H I know. V Snail is the thing I'm trying to solve for, but it's just a number. And Q, which is just a number. So I can do that integral. Okay, so I take this. And I plug it in. I'll write it out to give you a little more time to think about what the next step is going to be. Okay, so this is going to be 12 over h cubed times h times 1 minus v Snail over 2 minus q dx. Okay, so that's going to be equal to, I guess I'll do this out the long way to give you guys some time. So this is going to be 12 over h squared times 1 minus v Snail over 2 times this integral dx over h squared minus q times the integral from integral of 12 q dx sorry. Not allowed to do that, thanks. Good, okay, and so this is equal to 0. So cancel my 12. Okay, and in fact, I'll just set these two guys equal. Right, so now I'm going to call this, since I'm doing this in general for any foot shape, I don't really care what the foot shape is, I'm just going to name this integral. Okay, so this integral I'm going to name I2, and this integral I'm going to name I3. So given a shape of the foot, you can compute these integrals and they're just numbers. Right? And you can see what, actually I put the subscript. Okay, and you can see what my naming convention is. This is just I sub n is the integral over h to the n. Okay. Okay, so that's my next condition. We'll rearrange it, that's fine. All right, so I've now given you time to think about what the last thing I have to impose is, and so what's the last thing I have to impose? Can anybody bring their notes from Monday?
The summation of forces on the snail. That's
Summation of force on snail has to be 0. Exactly. Okay, so I have to do force bound on
cheated.
snail.
I have no
Excellent. Perfect. So force balance on the snail. So the force balance on the snail, the only forces acting on the snail is the force coming from the fluid. Okay? So the force coming from the, I mean, there's drag from the air, but the snails really aren't moving fast enough to really care about that. So the force from the fluid, it means that I have to integrate the traction force across the bottom of the snail. Okay, so the traction force is equal to sigma dot n. Okay, and remember this is a thin film, so there aren't going to be any large gradients. So you can assume that this n is going to be something very gradual, right? So which tells you that dh dx is small. Okay, so if you use that approximation, what you find is that the let's do this. The x component of this, so this is going to be the force per area, really a force per length because I don't care about what's going on in this direction. But so the force per area, what is it going to be? I think it's going to be p dh dx plus du dy. Right? And you can see where that comes from. If you just write out what the stress tensor is, you figure out what the normal vector is on a shape that looks like that. That's not very, very much. You get a force that looks like that. Okay, and now I just have to integrate this over the entire snail, over the snail foot, in order, well, I'll integrate it over one period in order to get the force. So f of x, which has to be 0, is equal to the integral from 0 to 1 of this stuff in here, integrated along the foot. Okay, so now we're almost there. Okay, so now what I'm going to do, I'm going to integrate this term by parts. Okay, so this is going to give me a pH from 0 to 1 minus the integral from 0 to 1 of h dpdx. Yeah, dpdx. dx plus the integral of u dy dx, and this has to be equal to 0. Okay, this guy is 0. Good. Periodic. Good. Be confident. 0. Okay. Good. Now what do I have left? So this guy here. So h is given. That's a function of x. The pdx I have over here, and I have it now in terms of h, which I know, vs, which I'm trying to solve for, q. Okay, q I now know. Right, so I have q in terms of vs and these integrals which I know. So q is no longer an unknown. So the only unknown in here is vs. So I can plug that in here. This guy over here, du dy. So u I have up here, and again, the only unknown, so dp dx I can put in from here. Vs is the thing I'm trying to solve for, so I have everything I know. So the only unknown in this equation now is v snail. So I can solve this for v snail. Okay. Okay, so let me just write down what the answer is. Without going through all the algebra. So if you write this out, you find, now this is where it starts to get good, that v snail is equal to 6 times 1 minus a divided by 4 minus 3a. It's a very small expression, okay. And a is equal to I2 squared dx over h to the n. Okay, so what this tells me is you give me a shape of the foot, you give me h, and I can tell you how fast this thing goes. Okay, you give me any shape and this is what happens. All right, so now we have to understand what this means. And there are a couple of actually interesting things in that, the structure of that answer over there. Okay, so first of all, A. So can anybody give me a bound on A? Somebody give me a lower bound on A. 0. Why is it 0 the lower bound on A?
Why?
Why? Yeah.
Because of that integral?
Yeah, and why? And what tells you? What about that interval tells you that it can never be negative?
The answer is
H can be any power. H can be odd powers as well as even powers.
But the coefficient's positive.
The coefficient's positive. The coefficient's root of coefficient.
Well, it's a 1.
1, right. So, well, if I mean, okay, I can give you all kinds of H's. It just doesn't have to be positive, right? But H is positive. Exactly, H is positive. Okay, so H is always positive, so it has to be positive. Okay, so, and right, H has to be positive, otherwise your snail foot goes underground. So, okay, so 0, so A is bounded from below by 0. So this is the harder bound. You know how H is bounded, A is bounded from above. This was actually pointed out to me by one of Mike's postdocs. Okay, this one's harder. Okay, so the upper bound you get by the Cauchy-Schwarz inequality. Remember that off the top of their head? Okay, and the Cauchy-Schwarz inequality tells you the following. So it says that, let me write it in terms of my eyes. Okay, so I2, I can write in this funny way. So I can split that up. I can split the inside of that integral up into h to the minus 1/2, h to the minus 3/2 dx. Okay, and the Cauchy-Schwarz inequality tells me that this must be less than or equal to the integral of h to the minus 1/3 dx times h to the minus 1 dx, which is equal to 1i. Oh, sorry, this is squared. Doesn't make any sense. Okay, so that tells me I2 squared is always less than I1 plus I1 times I3. So in my definition of A is bounded from above by 1. Okay, so A is bounded from above by 1. So that's great. All right, so let's think about what that expression actually looks like. Okay, so this is A, this is the snail, and I know A is going to go from 0 to 1. Okay, so when A is equal to 0, I have 6 over 4, so it's 3/2. This is 3/2. There's A is equal to 0. When A is equal to 1, it's 0. Okay, and if you plot it, you get something like this. All right, so your snail velocity, oh, I've done this totally backwards. Good. Okay, so the first thing it tells you is that if A, which is determined by the shape of your foot, approaches 1, your velocity is lousy. Okay, so now we have to think about what kinds of shapes map to A is equal to 1 and what kinds of shapes map to A is equal to 0. Okay, so it turns out that the shapes that put you down here where you want to be are the shapes that tend to be sharp. Okay, so let's say sharp foot shape means that A becomes very small. Okay, and by a sharp foot shape, I mean something that's got something pointy in the middle here. And Mike actually did a bunch of nice asymptotic analysis to figure out what kinds of families of shapes these are. Physically speaking, why would you expect this to be good? Well, the things that are pushing your snail, the thing that's pushing your snail forward is this pressure difference, right? And you get a big pressure difference if you have a tiny gap here. Okay? So this kind of shape gives you a big pressure difference, and that pressure pressure acts normal to the foot. So you want your foot to be sort of as vertical as possible here so your pressure can push in the direction that's useful. Okay, so that's the first thing. Yeah?
Just real quickly, so you did make the assumption that H varies slightly with X, but a sharp shape like this violates this assumption.
That's exactly right. That's exactly right. I'm going to write that down. That's so important. So, okay, but this violates our assumption that BH dx is small. Okay, keep that in mind. We're going to come back to that in a minute. Okay, so, right, so there's two reasons this is good. One is that the pressure is pushing in the right direction. The other thing is that you want to minimize viscous dissipation. So you want the regions where this thing comes close to the ground to be as small as possible. Right? So you want to make this as skinny as possible. You want to make this as vertical and as big as possible, which gets you shapes like this. Okay. So, let me come back to that in a minute. There's something else that's very funny about this plot. And now I've let you look at this plot right here. Let you stare at this for a little while. Does anybody see why there's something very bizarre about that plot? Particularly on the end where A is close to 0. So remember, what is my definition of Vs? It's a snail velocity, but it's been normalized by what? The wave velocity, right? Okay, so this is equal to snail over wave. Okay, so what does that actually tell you on this end of the plot?
You can be bigger.
The snail is moving faster than the wave, which is bizarre, completely bizarre, right? So I would have expected anything down here would have been okay, right? But so what does it mean to be moving faster than the wave? So, I mean, imagine this in the sort of the best case scenario, although now you know it's not the best case scenario. So imagine you had a tank. Instead of a snail, imagine you had a little tank. Okay, and this tank has a tread that's going like this and is running along the ground. Okay, and let's say that tank is running along the ground with absolutely no slippage. Okay, absolutely no slippage. So the wave velocity would be if I take one of these points and I follow it along the tread. Okay, so let's say I have a point on my tank tread that's moving with some wave velocity like this. Okay, so if there is absolutely no slippage, then how fast does the tank go? Be wave, right? That's as fast as it can go, right? Because if this goes this way and this goes that way, and there's no slippage. Okay, so what I'm saying when I draw this is I'm saying, well, okay, this thing is actually doing better than this because it's slipping forward. So it's going 50% faster than you would be able to do in the best case scenario with a tank. Sorry. All right. So when my graduate student first came to me with this calculation, I said it's wrong. Go back and find your factor of 2 and come back to me. And he said, no, it's right. He came back and he said, no, it's really there. And I said, no, it can't be. So go back. And so I said, okay, fine. So he finally convinced me this is right. I mean, there's not all, you've seen this, I've done all the algebra on the board. There's not that much to check, right? So, okay, so in this, so in this limit, this really does happen. So I said, okay, this must be what's going on. We violated something in our assumptions. These shapes that make it you to move so well aren't allowed. Okay, so we called Mike, and Mike and his postdoc John Wilkins had a very nice code where they could solve for the full Stokes equation with the layer. And so they did that calculation. So they had. I'd show you this movie if my computer hadn't died, but it's fine. So they did something like this. So they did this. They solved the Stokes flow for Stokes flow in here. They looked at material points on this thing and to see how they moved. And since this is now full Stokes flow, we don't care about any of these assumptions. We don't have to be careful about that. And they found this. It really does go faster. Okay.
So this is still the lubrication approximation?
This calculation is standard lubrication approximation.
Mike's calculation.
Mike's calculation is not lubrication.
I didn't understand what Mike's calculation is exactly. So what is it?
Oh, you just solve it. So you have a membrane here, and you dictate the kinematics. So you impose Get each of X and T. And then you have a fluid layer in here. And then you just solve Stokes' theorem.
I have the movie.
Oh, you do? Oh, good. So Michael shows the movie.
I'll wait till you're done.
No, you can come plug in while I'm talking. It's good. Okay, so Michael showed the movie, so you can believe that this really happened. Okay, so this is clear? Yeah, that's what he did. Yeah. Okay, good. So and unfortunately, that's all I can tell you. I don't know why it happened. So John Wilkening, Mike's postdoc, claims that he understands why it happens, but every time I ask him to explain it to me, he starts writing down equations. And I say, no, why does it happen? And
That's the way we are.
yeah, exactly. I know. I'm trying to break them of this. So anyway, so if you have ideas on this, you should let me know. And Mike's going to show you what the real flow field looks like when he plugs in. Okay, so now the problem, of course, is that this is not at all how real snails move. Yeah.
I just want to clarify, so the boundary conditions are periodic boundary conditions, even in like simulation?
Yeah. You'll see it right here. Okay, so the gray dots on the top are material lines that are attached to the boundary. So that's where the snail is moving. And then the black dots in here are particle tracers.
Should I go?
Yeah?
Oops. That's wonderful.
And you can see nothing happens. Easy.
It's like there's two movies on the screen, right?
Yeah. Well, what I'm going to do is I'm going to be brutal. Let's see. Let me go back and play it again.
Okay, so what you want to notice is that the gray points are moving faster than that dip is moving. Right? They're running ahead. They're running ahead of the deformation of the fish, which means that the thing has to be slipping forward. Play again.
Yeah, see, somehow it's kind of thrashing there.
Yeah.
I don't know why.
So you have fluid flow at the surface.
There's a no slip boundary condition at the surface, right? So since the snail is in fact actually this boundary is not moving at the same speed as this thing is, right? So it's like it's a sheet that's sliding along this shape.
I should just put this on.
Excuse me.
Yeah.
Well, the further you are from the boundary, from the wall, you expect to go faster, no? So if you're in that whatever that point in the groove, then you have to go more slowly than if you're actually on top because you're further from the wall.
Over in here. So what you're saying is that the flow velocities must be slower here than up here.
Yeah.
Correct. Absolutely true.
So and this is what we see here.
Yes, but notice again the funny thing. So certainly the structure of the velocity is exactly what you'd expect, right? Because you have no slip on the bottom, no slip on the top. The question is, I have got a snail up here that's propelling itself forward, right? And so I would have naively thought that the fastest you could push this thing forward would be the speed at which you're pushing this thing backwards, right? And that's not what we see. We see that this thing can actually move 50% faster than you're pushing back, than what you're pushing backwards.
But is that the same part of the snail the whole time? It's not, right? The belly is like.
So yeah, so this is the boundary condition. So we have to do a little bit of the boundary condition, right? So the boundary condition. Let me do it. So in the frame that we did the calculation, we moved into a frame such that this point is stationary. Okay. So while this point is stationary, the snail is still moving, which means that this boundary here has got some velocity going in that direction, right? So imagine you have a shape. So let's say I take a block of wood or something, I cut that shape out of it, and then I lay a membrane on this, and then I pull the membrane such that it's stuck to the shape. Okay, so your boundary condition at the top is, I pull this membrane at some v snail, which is how fast that top boundary is moving. So the boundary condition is a little subtle.
Mike's calculation was purely using string functions. Was this calculation using string functions and a boundary condition?
It's full Stokes. You can do it as a string vorticity if you wanted to.
It's a numerical calculation or?
Yeah.
Yeah. Yeah. Yeah, and I should say, you know, that it sits exactly on this, what we produce by lubrication. You know, eventually when this thing gets, if you put in something that looks like that, then lubrication is lousy, right? But it's remarkably good up to very, very sharp structures, lubrication approximation.
A question for Mike. The color of the movie, is that pressure?
I'm sorry?
Color of the movie, is that pressure?
The color in the
The color in
movie.
the movie, it's a vorticity, I think.
Is that, yes, it is vorticity. That's right.
Good, okay, so that's the puzzle.
Sorry, just one more thing.
Yeah.
So I think the snail is not riding the car, so it shouldn't go at the same speed, so it has to go faster. This is how I like intuitively.
So,
I just think
I
like
would say-
it should go faster because it's slipping on it. So I mean, just
So,
I
I
mean,
would
it's not that whatever thin layer of liquid is not like a car. It's not like something that you're riding with it and it's
So
always
I would
very.
argue that you have to go slower, because if, let's suppose I put something down here, and I have something that generates a wave on the bottom of this thing, and I put it on the thin film, right? So if it's slipping, then it shouldn't make any progress, right? It should just be running whatever its motor is, and why would it push itself forward if it's slipping? There's no reason, otherwise it would just take off, right?
In fact, it only goes faster once you have these
These
sets of
particular
shapes.
strange shapes, yeah.
Just take a sinusoid and
Yeah, the sinusoid goes to what you would expect, basically the tank treading condition where you're stuck to the.
So where's the crossover?
Yeah, go ahead and then you, yeah.
This crossover you do there
Yeah.
is pretty much close to A=1, right? So what are the shapes that correspond to that?
So actually, this is probably a little bit smoother. It's probably, it probably comes down sort of more like, kind of crossover kind of in the middle here. And so one of the shapes that corresponds to this is a sinusoid. Right, so if you take a sinusoid and you have it just touch down, then that gives you the snail is 1. And then as you start to sharpen it up, you start to move this. Yeah.
So, if you imagine taking the table, putting a bunch of round pencils on it,
Yeah.
and then take a book and slide along on top of those pencils, you would notice that the book moves exactly twice faster than pencils do.
Oh, it does.
Yes. So
Wait, what do you mean moves faster? Oh, I see, because the pencils are rolling like this. I
Yes.
see, yeah, okay, good.
And to me, it seems like almost the same thing here. Well, except there is some probably dissipation in the
Right, because you must have. That's actually a very interesting idea. So I haven't thought of it in that case.
And these dips in the interface
Yeah.
allow different velocities of the liquid on one side and on another
Right.
side. So that's the same as you imagine that pencils wouldn't touch each other and let rotate in one
Yeah.
direction or opposite.
Actually, I like that analogy. And you do see sort of rolls in that thin film,
Yes.
right? So.
Or the same analogy that you said with the tank.
Yeah.
It's the same if tank was fixed not to the wheels,
Yeah.
but if you take the tread and put the tank on top of the rolling tread.
On top of the rolling.
Well, if it's rolling, the top line would move twice faster than the front edge.
Yeah.
And then if you put something on top of that thing, that would move twice faster, well, until it falls down.
Actually, that's it, yes. Exactly. You have to have a very long tread. Yeah. So maybe we should look at the velocity field. Maybe that's it. Yeah.
The materials points are moving much faster than the wave speed,
Yeah.
right?
Yeah. 50%. Yeah. Well, it's 50% faster.
Like if it's a delta function, they're
Yeah.
moving much faster. So you're driving the flow with sort of surface velocities are much faster than the wave speed. I don't.
Sorry, wait, sorry, say that again?
So if you have a sharp spike, the
Yeah.
wave speed, the wave moves over slightly, but the material point hasn't jumped down.
Oh, I see. Yeah. So, yeah, I see what you're saying. I see, right, because over here, I have to be moving at some v snail, and I have to continue, I have to move at that same speed here, but I have to go much further, so I have to go very fast in that little region. Yeah, and I think that's what drives the vortex rolls next to it. Yeah, that's nice too. Good. That was good. You guys might have just solved that problem. Okay, cool. So, so that's snails. Actually, look at that calculation. That's a good idea. All right. So actually, this is not snails. Snails don't move like this at all. All right. So let me tell you how snails move. Okay. So the problem with this in snails is that so snails have this very thin film of fluid that they're riding on, and you know from doing these kinds of lubrication calculations that it's much easier to move this way than it is to move this way. Right? And to make these kinds of shapes, you have to be able to pull your foot away from the surface and move it back in. Right? And if you actually just look up the strength of the muscles in a snail's foot, they're not strong enough to pull their foot away from the surface. Okay? So the only thing a snail can do is it can move back and forth like this. Okay? So what a snail actually does is it has. Okay, so here's my substrate, here's my snail foot, and it sends a bunch of waves of expansion and compression along the bottom of the foot like this. Okay, and these waves of expansion and compression travel along the bottom of the foot. Okay, and now you can see there's a problem, right? Because now we're back to our problem of low Reynolds number where you have to break symmetry in the problem, right? Because if I just took a snail foot like this and I had expansion and compression, you're not going to go anywhere. Because every time you do this, then when you come back exactly where you started. All right. So the way you get around this in a real snail is, of course, that this fluid is not a Newtonian fluid. This is a non-Newtonian fluid. Okay. So let's see. So non-Newtonian fluid. So let's just do a quick back of the envelope calculation to figure out what you need to move. Okay, so my student Brian Chan decided to solve this problem by building a robot, and here's the robot he built. Okay, so he built something like this. It has a bunch of little pads. So I'm now looking at it from the side. So this is what the side of the robot looks like. These are little plates, like this. Okay, and they can move relative to one another in this direction. So here's the substrate. And you put this on a film of fluid. This. I'll do it. Okay, so here's my film of fluid. Okay, and then these guys are all attached together like this. All right, and so what you do is in the first step, you keep all of these guys rigid, and you apply a force between these two guys to pull them together. Then you make these four rigid, and you apply a force between these guys and pull them together. Then you make these four rigid, and you apply a force here, and then you make these four rigid, and you apply a force here. Okay? So you do that in sequence. So let's just think about what happens in the first step. So in the first step, all of these guys are rigidly connected. So this is one rigid piece. Okay? And you apply a force between this guy and this guy. Right, so this is the muscle. There's some motor or muscle here that will pull these guys together. So this is F, and this is F. Okay, so now I guess we could just write this down. So if I draw a little 3-line diagram of this guy right here, let me call this section 1, and let me call this whole chunk here section 2. Okay, so section 1. So if I do a force balance on this, so I've got F that's pushing in that direction. And F must be resisted by, the only thing it can be resisted by is the viscous shear in this layer. Okay, so the viscous shear in that layer is going to be mu times the velocity of that, let's call that velocity 1, divided by the thickness of the layer, let's call the thickness of the layer H. So that gives me a shear stress. I have to multiply that by an area, let's call that A. And so A is the area per pad. Okay, so each of these has an area of A, and let's say N is the number of pads. Good, okay. Now I'm going to do the same thing with this guy. It's exactly the same, but with a minus sign. Okay, so F minus F is equal to mu. V2 is how fast that thing is moving. The area now is going to be N minus 1 and A divided by H. Good. And I don't really care about the velocity of this pad or the velocity of this thing. What I care about is the velocity of the center of mass of the whole thing. Okay, so the velocity of the center of mass is just going to be the average of all of these pads. Okay, so the velocity of the center of mass is equal to V1 plus N minus 1 V2 divided by N. Okay, now I'm just going to write down the velocity of the center of mass in terms of these, all of these other things, the forces that I'm applying to this thing. Okay, so so I do a little bit of algebra. Maybe I write it down to get my minus signs right, but you can see it's like one line of algebra. So if you do that, you find that the velocity of the center of mass is equal to FH over AN, so there's some prefactor that comes out front, times, and this is the interesting part, it's going to be 1 over mu1 over mu2. Okay, and so, and notice that I cheated a little here, is I said, okay, well, I'm actually going to name this viscosity here 1, so that's the viscosity that pad 1 sees. And I'm going to name this viscosity 2. This is the viscosity that pad 2 sees. Okay? So the velocity of the center of mass. So this is the velocity of the center of mass of this crawler. It's proportional to the force that you exert. Fine, that makes sense. Proportional to the thickness of the film. Fine. Then you can put in sort of the geometric parameters of the crawler. But the interesting thing is this guy right here, which is that it also depends on the difference of the viscosities between what this guy sees and what this guy sees. And the only way you can have a difference in viscosities between what this guy sees and what this guy sees is if you have a shear dependent viscosity. Right? And so a shear dependent viscosity means that you have to have a non-Newtonian fluid. And furthermore, what this tells you is that it doesn't really matter what kind of a non-Newtonian fluid you have. As long as you have any kind of nonlinearity, that breaks the symmetry and you get something non-zero and this thing will move. And what's even more interesting is that the type of nonlinearity, so let's say I want to do shear thickening versus shear thinning, determines which direction it crosses. Because there's a minus sign here. So shear thinning is going to go one direction, shear thickening is going to go the other direction. Okay. And it works. We can put this, so we put the robot on fluids and it crawls in different directions, exactly like you'd expect. Okay, so so that's closer to what real snails do. Let me just describe one other calculation. I'm not going to go through the details, but I'm going to tell you what it is, just because the results are sort of interesting. Okay, so this is a calculation that was actually done by Eric Lauga. And Eric asked the following question. So he said, okay, this is fine. So, I should also tell you that if you do rheology on the mucus of real snails, it's extremely nonlinear. And this we know because there was a guy, Mark Denny. Actually, are you guys familiar with Mark Denny's papers? Okay, if you don't know Mark, I'm going to write that down. This is, so if you're going to look up sort of the fundamental references, like the textbook references of in biofluids, two names you absolutely need to know are Steve Vogel, which I think Jerry told us about yesterday, and the other one is Mark Denny. That's D-E-N-N-Y. So both of these guys write beautiful papers on sort of different scalings of biological systems. And Mark Denny, when he was a PhD student in the 80s, did his thesis on the rheology of snail slime. And he has many, many beautiful papers in Nature on the rheology of snail slime. And so we know that it's extremely nonlinear. Okay, so let me go back to the problem that Eric wanted to answer. So Eric asked the following question. He said, well, okay, if I think about how snails evolved, so snails have obviously evolved to make this very complicated rheology. It would be much easier to use water, so there must be a good reason to make this. So he said, okay, if I'm an evolving snail, what is the optimal rheology of the fluid that you should have, that you should use to crawl? Okay, so turns out, so the question we really wanted to answer was the following. All right, so Heinrich had these beautiful plots that he showed a minute ago. Okay, what you really want to know, so if this is stress versus strain rate, right? So a Newtonian fluid does something like this, right? So this is Newtonian. Okay. What you'd really like to know is if you're a snail, what shape you want this thing to be for an optimal snail. Okay, that's the question you really want to know. Turns out that question is incredibly difficult to answer, so we didn't answer that one. So Eric did the following calculation instead, which I think is in fact more biologically relevant. Okay, so the question he asks is the following. He says, suppose you're a primitive snail, and as a primitive snail, you don't know how to make these big complex molecules that go into making your mucus-bearing non-Newtonian. Right? You know how to make small molecules. Okay? So you start to make different small molecules, and you start throwing them in your mucus, and you see which ones work better. Okay? And as you evolve, you can evolve the structure of these molecules to do better and better. So he said, okay, so suppose I start off with something that is Newtonian, and I perturb the system a little. Is it more beneficial to do something that looks like this, or to do something that looks like this? Right? So one of them is going to be shear thinning, and one of them is going to be shear thickening. Okay? So, so you can do the calculation, and I'm not going to go through it because the algebra is fairly long, but the reference is Lava and Hosoi, Phys 2006. Okay, and if you're interested in this, the calculation is not hard. It's again a thin film calculation, and only now instead of having a Newtonian constitutive relationship, so instead of having something that looks like this, where my stress is proportional to my strain rate, Eric now perturbed that to put a little bit of perturbation on it, so you can something that's going to be some functional strain rate. Right, so so this is a small perturbation that goes on this, and then you just go through exactly sort of a similar calculation to what we just did with a thin film. So you scale it out, so you only get the nice terms that you care about, and you just have to carry this perturbation through. Okay, and so then the question is, which is better for the snails? So of course, so you can go through this. You can find velocities, you can find pressures, you can find everything that goes on in the thin film, and then you come to the end of the calculation, and you have all of these numbers, and you say, okay, now what does it actually mean to be better for the snail? What is the snail trying to do? Right? How can I tell which of these numbers is better? Okay, so Eric said, okay, well, let's think about two cases. So let's suppose that the snails are trying to be as efficient as possible. Okay, so let's say you're going to maximize for efficiency. Okay, so if you're trying to maximize for efficiency, again, you run into a problem. Okay, and the problem, so the first thing you try is you say, all right, let's suppose the thing you're trying to maximize is mechanical efficiency. Okay, so mechanical efficiency, that's whatever, you want to minimize whatever power the muscles have to put in relative to how fast you go. Okay, so if you want to just do it, so this is the same efficiency we talked about in the low Reynolds number swimmer. It's exactly the same as the efficiencies we defined on Monday. So this is a mechanical efficiency. Efficiency, you get a nice long expansion, which is written out in this paper, and you find that you are better off if you make your fluid slightly shear thickening. Okay, so that was the first thing you tried. But then the next thing you tried is, well, there's actually another complication in these biological systems, because the snails have to make this mucus as they go along. Right? And the mucus has got all of these big, complicated molecules in them, so it actually costs you a lot of energy to make this stuff. Okay? So you may be better off, instead of maximizing mechanical efficiency, to minimize mucus production.
Because you have to leave it behind?
So in general, snails do leave it behind. So and I'll tell you. So when you minimize mucus production, the flow that you get out of this is something where you are recirculating it, so you're dragging as much along with you as you possibly can. But since you have a no-slope condition at this surface, you're always going to leave a thin film. So this leaves as little as possible. Is what that calculation is. Yeah, so, and in fact, actually, this is why snails come out when it rains, because they need the water to hydrate their mucus. Otherwise, they can't make enough mucus.
Is it minimization at constant speed?
Yeah.
Because if it doesn't move,
Exactly, yeah, exactly. These are all for fixed velocity. Yeah, exactly, for fixed velocity. Yes, good, yeah. Yeah.
Were there any assumptions about the muscle pattern?
So in fact, actually, you can do it without making an assumption about the muscle pattern, other than it's a wave. So
is it an in-plane wave of compression?
Oh, sorry, in plane. So this is so we use the sort of the thing that you would expect from real snails, which is going to be always in plane. It turns out that if you allow it to go out of plane, you can actually correct for that, and it doesn't do much, and you will sort of know which way it goes if you put that in. Yeah. But the results I'm going to show you here was all in plane, but any shape of stress on the foot. Good. Okay, so if you want to minimize mucus production, what you end up with is that you want your mucus to be shear thinning. Yeah, shear thinning. Okay, so now we have a problem because we don't know which one wins. So we went and we looked at the papers of Gardeni, who, of course, like I said, did his thesis on the rheology of snail slime. And so he's actually measured the energy consumption in snails. If you go back and you look at his papers, he says that something like 90% of the snail's energy budget goes into mucus production. It's a terrible way to crawl. It's really inefficient. Okay. So that would expect. So you would expect then that the mucus should be shear thinning. And in fact, when you do the rheology measurements, it turns out to be incredibly shear thinning. You know. So it's all consistent. It's biology. So there are many pressures that were on the snail that caused it to evolve its mucus to whatever it is. But it's certainly consistent with these sort of principles of minimizing the energy production, that you need to move. So good. And so for the next 15 minutes, I would have showed you movies of snails, but you'll have to wait until tonight for that. So you guys have any questions? Yeah.
Why don't the snails try to maximize their speed for a given hour?
Yeah. So exactly. So
they're not known for the speed, but it's kind of
exactly. So the reason that's exactly the reason we didn't look at it. We decided that snails weren't really known for their speed, so they probably haven't optimized that in their evolution. I don't know how you build a speed snail. Yeah.
Are there animals that do this?
So yeah, okay. So so the answer is yes. So people have come to me and asked us to redo this calculation actually for cells, because cells tend to ride along our own until the fall and things on the fluid. We haven't done that yet. But in addition, there are a lot of marine animals that do this. And I think, so I don't know, but I suspect that one of the reasons snails evolved this way is that I think they were originally marine animals. And so your objective there is not really to move very fast, but it's to not get swept away. Right, so you want to be able to get stuck to a rock. So the question is, how can you transport yourself around when you glued yourself to a rock, right? And this is one way to do it, right? Because in any step, most of the foot is adhered to the surface that you're on, and you're only moving a small fraction. So your weight's walking away. Yeah.
What does this stress strain curve look like experimentally? Is it really just a simple curve, or?
Yeah, it's obviously very complicated, but it's I mean, it basically looks like a yield stress curve. So it's a very sudden thing. Yeah. Oh, I should say something else. Okay, so remember I told you the from this back of the envelope calculation that I erased, the rheology of the mucus tells you which direction your snail goes. Okay. If you look at land snails versus marine snails, land snails, the waves tend to go in the direction of motion, and marine snails, the waves tend to go opposite to the direction of motion. And so all of the rheology measurements we have are for land snails. And so I don't know if marine snails actually have a shear thickening mucus or if they do something else.
You could put them on a different liquid and see if they move opposite or something.
The marine snails?
Or land snails.
Oh, if you put, yeah, exactly. So you scrape off their mucus and you put them on something else. Yeah.
That works.
So the problem with that is that they're continuously producing.
They are producing it.
Right. So if you put it on something, then you right. Yeah, so.
Maybe you should plug your nose.
Yeah, exactly. Exactly something like that. Yeah. Yeah.
So if you have two snails racing each other, is it advantageous to go behind
Drag
it?
behind it.
One-
Actually, I think it is because you have to produce less mucus. And you can plug your, this is the disgusting part of snails, is that if they come across their old trail, they will sometimes reingest it so they can reuse it. Yeah.
What exactly is snail? Just other snails?
Oh, a snail bot. Yeah. So the snail. So we built a couple of robots that mimic. Is that what you asked about the snail robot? Yeah. That mimic this method of locomotion, and the reason we did it is because we wanted robots that climb walls, right? Because snails are, it makes climbing very easy because you basically glue yourself to the surface. And one of the big challenges in robotics is building robots that can climb walls. So, and the snails, you don't have to worry about balance, you don't have to worry about timing, you don't have to worry about torque coming off the wall because you just glue to it. Yeah. So we have a couple of snail bots that will. Actually, and this is also an interesting question. So it turns out it's easier to climb upside down across the ceiling than to climb walls, right? Because if you're climbing a wall, gravity is acting both to try to pull you off the wall because of the torque, and it's impeding your progress. But if you're on the ceiling, gravity is only acting to pull you off, but it's not impeding your progress. So they actually go much faster climbing inverted across ceilings. The robots, I don't know about real snails. We haven't time. We haven't raced them up Good. All right. Thanks. So.